Hey guys, this is your third and final video for the independent study unit. This one is called Zoltar Speaks, and props to you if you understand that reference. So in this video, our goal will be that you can predict the products of the 5 major types of reactions. You'll be able to use something called the activity series to predict if a single replacement reaction is actually going to occur. And you'll be able to predict the product of a double replacement reaction based on something called the solubility rules. Both of these sets of rules are something you can find on your formula chart, so I'll show you how to find that. And this is where we will focus most of our efforts, is having you be able to predict those products for both single and double replacement reactions. So what you begin with is really important. The reactants in the chemical equation can tell you a lot of information as to what is going to be the products from that reaction. So for example, in the second video we talked about synthesis reactions and how that's where you got 2 things coming together to form one thing. So if you're beginning with 2 elements or possibly a diatomic molecule, because that still kind of is considered the same thing as an element, even though it might be O2 or Cl2. If you have 2 of those things coming together, then you're setting yourself up for a synthesis reaction and you're going to get one product. It's a little tricky to predict what that single product is, and so we're not going to focus on that. But you should be able to identify if you have 2 elements, the product is going to be one product, or this is setting itself up to be synthesis. Same thing with decomposition, just kind of in reverse. If you're starting with a single compound, the only thing that can happen is that it breaks down into more than one product. So this thing would be decomposing into smaller parts. Again, sometimes it's not super simple to predict what those exact products are, and so that's not what we're focusing on in this unit, but being able to say, if I'm starting with a compound and nothing else, that my products are going to be more than one product, therefore this is a decomposition reaction. That is what I expect you to be able to do. Now, if you start with an element and a compound, then you should be able to recognize that this is something called a single replacement reaction, and that on the other side we're going to get a different element and a different compound, because this element is going to replace one of the elements in that compound. This is where we will use that thing called the activity series to be able to tell us what is going to be over on the product side. And we'll do that here in just a second, but that activity series thing, that table can be found on your formula chart. The next one is if you have 2 compounds reacting together, then one part of the compounds are going to swap partners, and we'll use something called solubility rules, which again can be found on your formula chart. We'll use solubility rules to predict what is going to be on the other side of that arrow. And then the last of the 5 types that we talked about was if you have a hydrocarbon reacting with oxygen, then the products of this are always going to be CO2 and H2O. And as a review, a hydrocarbon is some compound that has both hydrogen and carbon in it. And sometimes there's something else, like oxygen, as part of that compound. But usually we're looking at just carbon and hydrogen in that hydrocarbon. So a couple rules for predicting products. You have to follow the rules for that type of reaction. And again, like I said, we're focusing mainly on single replacement and double replacement reactions, being able to use the activity series to predict the products of a single replacement reaction, and being able to use solubility rules to predict the products of a double replacement reaction. The synthesis and decomposition, we're not going to go into the rules of how you predict those products. And combustion reactions, we know the products are always carbon dioxide and water. We also need to make sure that we're double checking for diatomics when we're writing our formulas, and that we've written the formulas correctly. Because if we don't write the formulas correctly with the correct subscripts, then when you go to balance an equation, you're going to not get the correct mole ratios. Okay, so let's kind of speculate on what products we would see if we take pure sodium, which is just Na, and we could put an S here to indicate that that is solid sodium. And we put that into pure water. So we're reacting that sodium with pure water. And for water, we use an L. That's the only time you're going to use an L. Any other time you have a liquid substance, you would use AQ because something has been dissolved in water. And that's what AQ stands for, aqueous. That was in the first video. So these two things are reacting together. And we kind of take a look, and I see that I have an element in sodium, and I have a compound with water. And so at this point, this should look like a single replacement reaction. You have an element reacting with a compound. So the products of this are going to be something as switching places. Now I'm going to rewrite this H2O as HOH for the purposes of showing you what actually happens. When you're swapping places, it's important in these single and double replacement reactions that you be mindful of the fact that the cation, or the metal, sodium is not a cation in its elemental state, but if it's in a molecule or a compound, it is going to form a compound, or I'm sorry, it will form a cation. So the cation here is going to only replace the cation in the compound. And in that case, that's going to be this very first hydrogen. So when these two things switch places, that's how you know what it's switching places with. So that sodium gets in here, and it takes over the hydroxide. Be careful about checking those charges. So this gives us NaOH. And then we're left with just hydrogen getting kicked out. And hydrogen is, of course, diatomic, so we'd have to put it as H2. And then you would need to go through and balance that at the end. So here's another one. Predict the possible products of the following reaction. Potassium oxide reacts with fluorine. So for potassium oxide, this is K2O. I know that because potassium is a +1, oxygen is a 2-. And then fluorine is F, but it's part of Brinkelhoff, so we would put the subscript 2. And again, same thing like in that last one, we have an element reacting with a compound. And so this is setting itself up to look like single replacement reaction. So again, just like I said, if you have the element, if that is a metal, it is only going to replace the metal in the compound. If this is a non-metal, it will only replace the non-metal in the compound. Fluorine is in fact a non-metal, which means it would form an anion in a compound, and therefore it's only going to replace the oxygen in the compound. So those are the things that you switch. So oxygen is going to get kicked out to be by itself. Oxygen is diatomic. So we got O2. And then potassium and fluorine get together, and they are KF, because fluoride is F to the -1 and potassium is K to the +1. So when those come together, it's KF. And then you would need to go back through and balance this equation to have it fully correct, to have all your correct mole ratios. But there are the predicted products of this reaction. So the activity series, think of the activity series sort of like a ranking system in terms of if you were a boxer or a race car driver or a basketball player. The better your statistics, the more wins you have, the more free throws you make, the higher your batting average, the higher you are in the ranking system. And so lithium up here at the top is the most reactive. Basically what this means Sorry guys. Basically what this means is lithium is very unstable by itself. So if lithium has the opportunity to replace something in a compound that is below it in this activity series, it is going to do that. It's kind of like saying lithium is stronger than everything else. And so if lithium wants to be in the compound, it can kick anything else out of the compound in order to take its place. So this is something we use for single replacement reactions only. And I kind of emphasized how it's important that you pay attention to the metal replacing a metal or a non-metal replacing a non-metal. Notice this is the activity series of metals. So this is only going to apply if your single thing or the element in the reaction is a metal. You can use the activity series. And you can find this on your formula chart. There on the back. So there's the exact same thing that you have in this list. Increasing activity with lithium up there at the top. But what if you have something that's a non-metal, like that last example we did? Fluorine was a non-metal, and we had to figure out if it was going to be able to replace something else. Well, this is the activity series of non-metals. These are the four that we usually see, and there's not really much to memorize here because this is the way they appear on the periodic table. So fluorine is there at the top with chlorine underneath it, and then bromine, and then iodine. So fluorine is going to be more reactive or stronger, more able to replace anything that's below it. And here's the thing. If the stronger thing is part of the compound already, if the more reactive metal or non-metal is part of the compound already, aka it's not single, then we can do something called no reaction. Nothing is going to happen if, say, lithium is already part of the compound and sodium's trying to get in there and replace it. Sodium's not strong enough to do that. So we actually say no reaction. So let's practice one of those. So we're going to predict if the following reaction can actually occur. So we have barium plus iron 3 nitrate. So again, this is an element reacting with a compound. So this is quite obviously a single replacement reaction, which means we need to look to our activity series to figure out what's going to happen. So we check our single thing, and this single thing is a metal, which means we can use our activity series of metals. And we find barium on here. So there's barium. And then we check the metal that's in the compound, which is iron. And so we find iron on here. And so again, what this activity series means is that the higher they are to the top, the less likely they are to want to be alone. It's more reactive. So barium is above iron, which means barium is going to boot iron out, kick iron out of this compound, and barium is going to take over because barium wants to be in a compound more than iron does. And so the product that we're going to get is iron by itself, and then we have to use our ionic formula writing rules to figure out what's the compound formed between barium and nitrate. So barium is a 2+ charge, nitrate is a 1-. When you swap and drop, you get a formula for that of BaNO3 subscript 2. Then of course you would want to go back through and balance that equation for full correctness. Here's another one. Predict the products, if any, for the reaction shown below. So now we have magnesium, Mg, reacting with calcium carbonate, CaCO3, because calcium is 2+, carbonate is 2-. So now we're going to see if this is possible, if this reaction will actually take place. So we look for our single thing, which is a metal. We find it on here. There's magnesium. And then we look for the metal that's in the compound. There's calcium. And we notice that calcium is higher than magnesium. Calcium wants to be part of this compound. Magnesium also wants to be part of this compound, but magnesium is not as strong as calcium. So what that means is since calcium is higher up, that no reaction happens. Magnesium is not strong enough to replace calcium in this reaction. And so you can write no reaction, and that is a perfectly acceptable answer. No reaction. Nothing happens when you mix these two things together. So the last one, please try on your own. Pause the video, take a minute to jot it down. If you struggle or have questions, then certainly go in and see your teacher. Okay, solubility. Solubility talks about when you take a solid and dissolve it into a liquid. And not all solids will dissolve in a liquid. Not all solids dissolve in a liquid the same amount. Like some solids will dissolve a little bit and some solids will dissolve a lot. A term here that you guys kind of need to understand is this word dissociation. So when you take an ionic substance, it will dissolve to some degree, sometimes a lot, sometimes a little, and it does this thing called dissociation. So if I take NaCl, so think table salt from your little salt shaker, and I drop it into a glass of water, eventually you stir it around and it dissolves and you can't see any of the little white chunks anymore. And so what's happening on the microscopic level, if we could zoom in and see what's going on, that NaCl has done something called dissociated or ionizing, which means now it's got Na pluses and Cl minuses floating all around in this glass of water. So these ions are floating all around. So that is kind of the premise of where we're starting in terms of solubility. So some vocab that you guys need to be familiar with. In the first video, we talked about what aqueous means. That means something is dissolved in water. That is soluble. Do not confuse a parenthesis S with meaning soluble. That means solid, and that is not the same thing. Aqueous is the symbol we would use to indicate that something is soluble or that it dissolved. So it has dissolved in the solution. Insoluble means it does not dissolve. Does not dissolve in the solution, and that is where we use the S to indicate that it has formed a solid. It does not dissolve. And so if I pour something that is insoluble in water, I take a substance and I drop it into water, and it's insoluble, it will not ionize. It will sink to the bottom, and you'll see all the little crystals laying there at the bottom, and those little crystals would be the insoluble part of this reaction. Now, when I take two liquids or two aqueous solutions and I mix them together, pour them together, sometimes I get a solid. And so this is the insoluble solid, the insoluble product, and we call that thing a precipitate. So if a precipitate forms, that's where you have an insoluble product. That's important to make sure you understand those wording, because a common mistake is for students to think that this S means soluble, and it's not the same thing. Soluble means aqueous, that it does dissolve. So your solubility rules are also on your formula chart. And I'm going to walk you through how you can read these. There's a set of rules for things that are always soluble. There's a set of rules that are for things that are soluble with some exceptions. And then there's a set of rules for things that are insoluble with some exceptions. So as long as you know how to utilize this table, you should be A-OK. Okay, so kind of revisiting that conversation about a precipitate. If no precipitate forms when you mix, or when you have a double replacement reaction, that is the same thing as saying no reaction, because we're not actually forming a new product. And if nothing new is formed, then there's no chemical reaction that took place. If you do have a precipitate formed, then the double replacement reaction is said to have occurred, and that's when you need to use your solubility rules to predict what those products are. And it's important that you indicate which products are aqueous and which products are solid. And remember, this means soluble and this means insoluble. Okay, so let's try one. Predict if a precipitate would form from the following reactants. So we have MgNO32 and KClO4. So this is a compound reacting with a compound. And so you should be able to see this now and say, well, that's a double replacement reaction. And if it's double replacement, then I'm going to have to use solubility rules to figure this out. In a double replacement reaction, we're switching partners. So first step would always be to go ahead and switch the partners and see what you anticipate the products to be, keeping in mind that the cation can only switch places with the cation. So we could never have two cations together. You always have to have a cation and an anion together in a compound. Also keeping in mind that you have to pay attention to your formula writing rules. You got to check the charges and do the swap and drop to make sure your subscripts are correct. So we're going to switch these partners. So Mg is a 2+ charge. That's going to go with that ClO4, which is perchlorate, and that's a -1 charge. So when I swap and drop, the formula for that is MgClO4 2. And then the potassium, which is a +1 charge, is going to go with the nitrate, which is a -1 charge. Swap and drop, which is going to give me KNO3. So these are our products. Now we have to check to see if one of them is an insoluble product. Does it form a precipitate? Because if it forms a precipitate, then we'll just write which one is solid and which one is aqueous. If it does not form a precipitate, then we would say no reaction because we have not formed anything new. So, using our solubility rules, looking at this first one. So there's a system of rules up here at the top. These are the always soluble no matter what. Alkaline metals, nitrates, any of the chlorine-containing polyatomic, so hypochlorite, chlorite, chlorate, and perchlorate, ammonium, and acetate. If you have compounds that have any of these things in it, they are soluble, which means they do not form a precipitate. So in this very first reaction, magnesium is not part of any of these rules. That's in group 2, but perchlorate is. So since perchlorate is part of this compound, this is soluble. And we could indicate that by putting an AQ out here to tell me that that is aqueous. It will dissolve in solution. Then let's check this next one, KNO3. K is part of the alkali metals, that's group 1, and NO3 also appears on here. So what that means is this is also soluble or aqueous. And so now that I've figured out that both of these are soluble and aqueous, and there's no precipitate, then you can say no reaction. None of what we just did matters because we're not actually forming anything new. No reaction on that one. Let's try another one. So now we have calcium carbonate reacts with ammonium chloride. So the calcium is Ca2+, carbonate CO3 2- to give us CaCO3. Ammonium is NH4 NH4 plus. Chloride is Cl minus. So we get NH4Cl. Those two things react together. We're going to go ahead and anticipate what the products are of this, and then we'll check our solubility rules. So the metal, or the cation in this case, is going to swap places with the cation. So we'll trade partners, still mindful of our charges. So CaCl2 now, because Ca still is a +2 charge, chlorine is still a -1. So when we trade partners, those subscripts are changing. And then ammonium carbonate, NH4,2CO3. Alright, so there's our anticipated products. Now we got to check them against our solubility rules. So calcium is not one of the alkaline metals, and there's nothing up here that says anything about chlorine being soluble all the time. So then I can go check my other parts of my table. So this says that chloride ions are soluble unless, or with the exception of, if the chlorine is combined with silver or lead. So here's my chlorine, but it is not combined with silver or lead, which means this is soluble. It did not meet one of those exceptions, so this is AQ. Then I check this other one. There's ammonium here, and ammonium is one of the ones that is always soluble, so this guy is also soluble, which is AQ again. So what does it mean if we have two aqueous solutions? Nothing is a precipitate. We have no reaction. Let's do one more. So we're going to predict if a reaction occurs between silver nitrate and zinc 2 chloride. So silver nitrate, silver is Ag+1, nitrate is NO3-1, so the formula of that would be AgNO3. Zinc 2 chloride, Zn is 2 plus. This is not technically necessary because we know zinc is always 2 plus. Chlorine is Cl-1, so the formula for that would be ZnCl2. We'll go ahead and swap our partners to anticipate what these products are. So we'll get AgCl and ZnNO3, 2, and then refer to our solubility rules. So chlorine is on here under the soluble with exceptions section. So it's soluble unless it's bonded to silver or lead. And in this case, it is bonded to silver, which means this guy is insoluble. It is not soluble. So we would indicate that with an S to show that that is a solid product being formed. And then this one, the nitrate is up here in the soluble all the time section. Doesn't matter what it's bonded to, so it is soluble. And we would write an AQ to indicate that it does dissolve in the solution. So since we do get a solid precipitate or an insoluble product, then this would be the answer. This reaction does take place because we're forming something new. This is a new product, and so this is proof that this chemical reaction actually occurs. So this would, in fact, produce a chemical reaction. You can't say no reaction on this one. Don't forget to take a picture of your notes, submit them to the Google Classroom, and then ask your teacher if you have any questions.